Welcome to my video on normal distributions. I am Heather O'Brien. This will be a brief explanation of normal distribution and is intended to go along with the note guide provided to my students. The graphs of a normal distribution are a bell-shaped curve called normal curves. As you can see, it kind of looks like a bell. A normal curve is a smooth bell-shaped curve that depicts frequency values distributed symmetrically about the mean. So our mean is right here, and as you can see, if I folded about the mean, it would be symmetric on either side. The mean, and mode all will have the same value in a normal curve. The curve extends indefinitely in both directions and gets closer and closer to the x-axis, but never reaches it. The curve is symmetric about its center point, but not all symmetrical distributions are normally distributed. On a normal curve, about 68% of the data lies within one standard deviation of the mean. So as you can see here in blue. And 95% of the data lies within two standard deviations. So the yellow and the blue together would be 95% of the data, which is two standard deviations below and two standard deviations above the mean. And 99.8% of the data lies within three standard deviations, which is what that green arrow is trying to demonstrate there. So this gray part that's right there, the yellow and the blues, lie within three standard deviations of the mean. So that's 99.7%. So almost all of your data will lie within three standard deviations of the mean. The percentages represent approximations of the total percent of area under the curve. Let's look at this example. Suppose that a group of 200 students is asked their teacher to grade on a curve. If the mean on the test is 71 and the standard deviation is 7, the graph shows how the grades could be assigned. So our mean being 71 is going to go right here. A standard deviation of 7 means we're going to add 7 to 71 to get one standard deviation above, and we're going to subtract 7 from 71 to get one standard deviation below. So in other words, from 64, one standard deviation below the mean, to 78, one standard deviation above the mean, 68% of our data will lie. If we subtract 7 twice from 71, we'll get two standard deviations away from the mean. So 71 minus 14 would give us 57. If we did the opposite and took 71 and added 7 twice, we would be adding 14 and get 85, which is two standard deviations away from the mean. So if we use this to assign A's, B's, C's, and D's, it would mean that you got higher than an 85, you would get an A. If you got between a 78 and an 85, you would get a B. Between 64 and 78, you would get a C. Between 57 and 64, you would get a D. And less than a 57, you would get an F. So that's what grading on a curve would look like if we were using the normal curve to find our approximate grades. In this example, we're going to look at when a standardized test was scored, there was a mean of 500 and a standard deviation of 100. So we probably want to highlight that. There was a mean of 500 and a standard deviation of 100. Suppose that 10,000 students took the test and their scores had a bell-shaped distribution, making it possible to use a normal curve to approximate the distribution. That is why I have drawn the bell-shaped curve at the bottom as a way to approximate our answers. So the first thing we want to do is put our mean on our number, or on the number line for the bell-shaped curve, and the mean was 500. So right here in the center, we're going to put 500. Now, in order to find what's to the left and to the right, we're going to use our standard deviation of 100. So if I take 100 away from 500, I'm going to get 400. And if I add 100 to 500, I'm going to get 600. So 400 and 600 are within one standard deviation of the mean. So then I want to go out to 2 standard deviations away from the mean. So I subtract 100 twice from 500 and I will get 300 and 700. Now then I subtract 100 again and I will get 200 and 800. So we're going to use these numbers to help us find the answers to the questions above. And again, how we got those is we looked at our mean of 500 and we added and subtracted our standard deviation of 100 to get those numbers along the axis. And I do know that this looks like it's touching. It really isn't supposed to be touching the x-axis. It was just the quick drawing that I grabbed. So we're going to start by looking at letter A, and then we're going to go to each of these. We're going to make a drawing for each of these, shading the bell-shaped curve that is actually going to help us answer each of the questions. So for part A, it's asking how many students scored between 400 and 600. So on my bell-shaped curve, I'm going to mark off 400 and 600. And I want to know between there, so I'm going to grab my shading and I'm just going to shade. Basically, I'm trying to find the area under the curve for this part. Okay, so since I know that it is within 1 standard deviation below and 1 standard deviation above the mean, I can use the empirical rule that tells me that 68% of the data lies within 1 standard deviation of the mean. So we can say that 68% of the students, and there are 10,000 students. So 68% of 10,000 students is going to give me a total of, so 68% is 0.68 or 68 over 100, multiplied by 10,000 would be 6,800 students. That are going to be scoring between 400 and 600. For the next problem, we're looking for how many students scored between 300 and 700. So we find 300, make a line. We find 700, make a line. And since it says between, we shade everything in between. So we're looking for what percentage, first of all, students fall in this, and then we'll find, after finding the percentage, we'll figure out the exact number of students. Recall from earlier that our empirical rule told us that 95% of the data lied within 2 standard deviations. So since 300 is 2 standard deviations below the mean, and 700 is 2 standard deviations above the mean, it means that I know that 95% of my data lies between there. So 95% of the students, and there were 10,000 students, are going to have scored between 300 and 700. So 95% is 95 over 100, or 0.95, multiplied by 10,000 is going to give you 9,500 students. That scored between 300 and 700. On our next question, we're looking for how many students scored between 200 and 800. So 200 and 800, and everything in between I have shaded yellow. So we need to go back and think about that 200 is 3 standard deviations from the mean, and 800 is 3 standard deviations. So from 200 to 800, can we figure out what percentage of the data is lying under the curve? Recalling from earlier, we have this lovely normal distribution in the approximations that 68% of the data lies within 1 standard deviation, 95% lies within 2 standard deviations, and 99.8% lie within 3 standard deviations. So that means that we have 99.8% of our data lying between 200 and 800. So 99.8% of all our students, and there were 10,000 of them. So that would give us how many students? So 99.8%, or 99.8 over 100, or 0.998, however you want to write it, times 10,000 is going to give you 9,980 students scored between 200 and 800. And the last question is a little bit different. It says how many scored above 800. So we're going to find where 800 is, but we're going to shade above it. Remember, that is a very small amount and the little tail of this. So I'm going to reference back to our normal distribution in the empirical rule, and we'll notice that we're talking about this small percentage right here. So since 99.8% lies here, then there's 0.2% that lies between the lower tail and the upper tail. So if we're only interested in the upper tail, that's going to be 0.1% of our data, or of our students. So we would say that how many students scored above 800 would be 0.1% of 10,000. So 0.1% is really, you still have to divide by 100, so move your decimal point 2 places and get the 0.001 times 10,000, giving us only 10 students.